Good morning, everyone. So let's start this morning with network virtualization in the context of multi-tenant data centers. And as you can see, this work comes with a rather long list of authors. And it's simply because this work happens to span about 5 years of calendar time. And this also happens to imply that there's a lot to cover here. So even just to give you an overview of the system we've built. So please bear with me. This might be a bit dense presentation. Now, the first obvious question you may have in your mind at this point of time is that, isn't network virtualization already solved problem? We have the virtual LANs, VLANs. And in fact, it's not just the VLANs we have. We can virtualize quite a few aspects of networking at this point of time. With VLANs, we can virtualize the broadcast domain. With network address translation, we can virtualize the IP. We can share the IP basically among multiple users. With MPLS, we can virtualize paths across your physical network. With VRF, we can have virtual FIPS in your router, and you can even run routers inside VMs if you so wish. And even more recently, the idea of slicing your OpenFlow hardware switch among multiple controllers has been proposed. Now, unfortunately, all these proposals are nothing but just point solutions in the sense that they address aspects of network virtualization. They virtualize single individual aspects of networking. They don't really provide a complete solution for network virtualization. And it turns out that multi-tenant data centers are exactly the place where these primitives alone are not enough to virtualize the network. So what is exactly a multi-tenant data center? Well, obviously, the data center has physical servers running the tenant workloads, and the servers are connected by a physical network which is built on a factory topology of some kind. And the physical network uses heavily multipathing to provide highly reliable, high bandwidth connectivity between the servers. And then the provider runs some server virtualization layer on top of the servers to host the tenant VMs. Now, if the provider would use the mechanisms alone I described or mentioned earlier to construct virtual networks for tenants, the result actually would be fairly challenging to operate. It would be difficult to place or move VMs around the data center because the tenant addresses actually would be present in the physical network. The addressing itself might place constraints where the VM can move. And it would be also difficult to provision new tenants since there's a lot of manual hardware configuration involved. All in all, the tenant workloads would be very, very much coupled to the physical infrastructure. And the operator would have not the flexibility to operate his infrastructure in the most efficient way, which actually is the whole point of having a multi-tenant data center. Now, to understand exactly what we are missing, let's look at the standard server hypervisor. Now, one can run his preferred virtualization software nowadays on a standard x86 server, and at most you need a bit more memory and CPU perhaps. It's the virtualization software on top of the hardware that actually provides the virtual machine abstraction, which then provides basically x86 interface for the applications running within the VMs. So what's relevant here really is the decoupling. The virtual workloads do not interface with the physical hardware directly. They only interface with virtual devices, virtual NICs, virtual storage devices. And it's exactly that decoupling that allows the operational freedom. The operator can stop, start, migrate the VMs, and applications within the VMs remain completely unaware of all these operations. So we need something similar for networking. On top of the standard switches and routers, we need a layer that actually allows us to build virtual networks that have identical features to physical networks, so that the workloads don't really know the difference whether they're running on top of a physical network or a virtual network. And if you're able to do this without any coupling to the physical networking infrastructure, we can move workloads, evolve the physical configuration, and keep optimizing the physical network without any implications to the virtual networks. So in the rest of the presentation, I'll first go over the network hypervisor we built, NVP, or Network Virtualization Platform as we call it. And I summarized the major challenges we faced while implementing the NVP, and then continue with the hard lessons we stumbled into while we're deploying NVP with our customers. And then hopefully in the very end of the presentation, I conclude with more surprising implications of network virtualization and how it's already changing the way tenants actually reason about networking. So let's look at the network hypervisor in more detail. Regardless how it's actually implemented, and I haven't talked about how to implement it yet, the network hypervisor has the responsibility to provide few key interfaces for the tenant. So first, for the tenant workloads, that is for the TCP/IP stacks within the tenant VMs, the network hypervisor has the responsibility to provide a packet abstraction that basically establishes a network view for the VMs as if they were running in a similar physical network. That is, the L2, L3, and the service semantics have to be identical to the corresponding physical network so that we don't have to assume any changes from the endpoints within the VMs. So for instance, ARP with IP and Ethernet has to be exactly the same. IP forwarding has to function just like before. And then, for the tenants to actually manage their logical networks, the network hypervisor has to provide a control abstraction of some kind. After all, the tenants are expected to manage their networks by themselves without any involvement of the physical provider. And it's actually only these two interfaces in the network hypervisor design that are really fundamental. So let's look at them more carefully. So as said, the packet abstraction is something we have very little control over. We effectively have to remain compliant with the legacy protocols running within the endpoints inside the VMs. With control abstractions, it's less obvious because there's really no universal high-level control interface in networking. It has always been traditionally about command line interfaces. But there is one low-level interface, though. And if you think about how the physical switches and routers are made, there's always a data path, an ASIC, which is in the end nothing but a packet processing pipeline, a sequence of flow tables, which are programmed by the local control plane. And that's it. It's exactly this data path, this pipeline of flow tables that we make the central abstraction in our network hypervisor. So in the end, our goal is to actually construct logical data paths which have logical flow tables so that the tenant control plane can then program the logical data path with logical flow entries that actually implement the exact forwarding behavior within the virtual network the tenant needs. Now, we don't expect the tenant to provide us a control plane binary of any kind, but we will instead provide the tenant with standard control plane implementations for logical switches and routers. So why is this abstraction of a logical data path so powerful? Now, if you think about a physical network topology and how a packet traverses through the physical network, while that happens, the packet actually traverses through a sequence of table pipelines or a sequence of data paths. It's the previous data path that makes a forwarding decision, which is the next data path to traverse, so that the destination can eventually be reached. That means that to provide arbitrary logical networks for tenants, all our network hypervisor has to provide is this virtual tenant-specific data path and the ability to interconnect multiple of them. With this logical data path, we can then provide a logical network just with a single logical switch, or we can provide logical networks with multiple tiers or any kind of complicated topologies. And since we are building these logical networks using exactly the same base construct as the physical networks use, the service model of physical networks is actually established quite naturally within the logical networks. So in the previous slides, I didn't say how and where to implement the network hypervisor. I only described the abstractions the network hypervisor should provide to both be general and faithfully model the physical network service model. And in our implementation, we actually picked an approach that doesn't touch the physical network between the servers at all. Instead, we leverage the virtual switches running within the server hypervisors and then just interconnect them over IP tunnels. The virtual switches are programmed by a centralized controller cluster, which is also responsible for running the tenant-specific control planes, which then program the logical data paths provided by the network hypervisor. So now, again, we are not assuming that the tenant would bring any own control planes, but the controllers really just have these standard control plane implementations for tenants to use. So This arrangement has some nice benefits. We really don't ask anything else from the physical network besides just the basic IP connectivity because we use tunneling. And we can also easily provide the tenants and the cloud management systems with these programmatic APIs. And we can actually provide tenants with interfaces to save the network configuration, snapshot the virtual network state, introspect the network state, and so on. And finally, as long as the source hypervisor tunnels the packet directly to the destination hypervisor, we actually have no other x86-based packet processing on the path of the packet besides the source and the destination hypervisor, which are on the path anyway. Now, this approach actually places a lot of pressure on the virtual switch, because in this approach, it's the first hop virtual switch within the source hypervisor that has the responsibility to implement the complete logical network and all the logical data paths and all the logical flow processing the logical network is made of. And we have to do this because we have to execute all the logical forwarding decisions before we actually know the logical destination port the packet is heading to. And only once we know the logical destination port, we can figure out which is the destination hypervisor the packet should be tunneled to. So here we have a packet that traverses through a logical switch to a logical router and then to a logical switch before it actually reaches the destination VM on the right side. And let's see what happens within the first hop virtual switch. So the packet processing is implemented as a sequence of flow lookups. When the packet is received from the VM, the first flow lookup basically does nothing but just identifies the logical ingress port and then basically feeds the packet into the first logical data path, which basically is a sequence of flow lookups. And the first logical data path, as a result of these flow lookups, comes up with a forwarding decision, logical forwarding decision that basically defines the next logical data path. And once we have identified that, we move on to the second logical data path, execute the flow lookups there, and so forth until we arrive with the third logical data path that actually comes up with the final destination port in this case, and then we can tunnel the packet directly to the next or to the receiving hypervisor on the other side of the physical network. Now, like I mentioned, it's the controllers that are responsible for the overall state computation and management in this sort of a system. And given the current location of the VMs, and given the current logical configuration and the physical configuration, it's the controllers that are responsible for computing all the forwarding state for the virtual switches and pushing it down into the hypervisors. And they have to keep re-evaluating the resulting forwarding state in case there are some changes, some configuration changes in the system. At the same time, the overall state we are dealing with is actually n-squared, has n-squared complexity. Because as you remember, the packet traverses the whole logical topology already at the first hop hypervisor, at the source hypervisor. So basically every single virtual switch needs all the forwarding state the packet may touch while within that logical network. And since there are n logical ports within a single logical network, each VM now basically has ON state, and the overall state in the system becomes n-squared. Now, we can't really aggregate the forwarding state because we prefer not to take any extra x86 hops beyond the source and the destination hypervisor. So therefore, we just have to live with the fact that we have a huge volume of state within the controllers. And to avoid recomputing all the state after every possible tiny change in the configuration or VM movement, we make the computation of the forwarding state incremental. So this is just like with the routing protocols. Every incoming change basically causes an incremental reevaluation of the produced forwarding state. Now, unfortunately, implementing incremental computation actually translates quite easily to finite state machines, which are very complicated to design, right, and especially to maintain in presence of asynchronous events. So we used an alternative approach instead. So we modeled the whole logic computing the forwarding state using Datalog, which actually quite naturally provides you with the incremental computational model, as well as, more importantly even, it lets the developer avoid reasoning about the ordering of events and just focus on the invariants that should hold all the time. And Since the number of hypervisors managed actually may still overwhelm a single controller, we use clustering and we shard the computation across the controller cluster, basically using the logical data path as the unit of sharding. So in many ways, the overall system I described is fairly simple, but there are some non-obvious hard lessons that we learned on the way. And the first one being that the logical abstractions provided for the tenant VMs, it's not completely obvious. It wasn't completely obvious in the beginning what should be the abstraction. After all, you can connect all the endpoints just by using a single logical switch if you so decide. As long as the switch is able to scale, that's fine. You have the connectivity. And that's actually enough for simple applications, but it turns out that more complicated applications actually may span several VMs, and once they do that, they start to embed some assumptions about the network they operate. So for instance, if you have a web tier application, it may assume certain level of isolation between the tiers. And in the worst case, it might be so that you cannot even change the topology of the workload without a lot of extra work. So for instance, it might require you to recertify the whole network topology, which would be the case in case you would actually migrate an entire bank, say, on top of the cloud. In that sort of an environment, even tiniest change to the network topology itself requires recertification. So that said, designing for arbitrary logical network topologies actually turned out to be a valuable early design decision we got right. So what didn't we get right then? Logical centralization turns out to be complicated from the failure isolation point of view indeed. It's not just enough to make the controllers highly available, but you have to be careful with the protocols running between the controller cluster and the switches. And in our case, we started with two protocols, OpenFlow and OVS database protocol. And in our case, OpenFlow wasn't providing atomic updates. So what could happen is that OpenFlow connection died in the middle of updates being pushed down. Either there was a network issue or the controller died or something else. And basically, as a result, the virtual switch could enter into an undefined state, which in the end, in the worst case, can mean that because you're using some sort of a mixture of old state and a new state, you could violate some basic security isolation assumptions we provide for our tenants. So for this purpose, we are moving towards a single protocol that provides the ability to push transactions down. And then, at most, the switch can be using old state, but at least it's not using any kind of incomplete hybrid of old and new state that could violate the policy guarantees we provide for the tenants. And the final lesson relates to OpenFlow. To put it simply, OpenFlow is just very, very expensive protocol that's run at scale. In our case, we are managing thousands of hypervisors, not tens of thousands of hypervisors, and even then, OpenFlow is starting to limit the overall scale of the system. Because if one uses OpenFlow to express all the data plane operations, expressing fairly simple operations actually can take quite a few flow entries. It could take even long lists of actions as well within the flow entries, and these all complicate the overall computation. And what's worse, the flow entries may actually be very redundant. And OpenFlow is also very tightly coupled with the switch, and what I mean by that is that to compute some entries to the switch, some flow entries to the switch, it actually might require you to first interact over OVS database protocol before you can produce these flow entries. So for these reasons, we are actually in the process of replacing OpenFlow and OVS database protocol with something more specific to the network virtualization. Now, it doesn't mean that OpenFlow goes away, it just becomes an internal protocol running inside the hypervisor. So in many ways, our guiding principle has been that we don't really modify the workloads, but instead we provide exactly the service model they expect. However, once the network virtualization is deployed, the best practices actually start to evolve further. And we are already seeing this. So for instance, we see workloads with network configuration that is basically a complete mess. The addresses and the topology in the workload actually have very little semantic meaning anymore, and it might be so that you are defining your security policies over pairs of IP addresses. So while we cannot do anything with these addresses, because we can't modify the workload, we can introduce out-of-band fields with the network hypervisor that are not visible to VMs. And that way, we can actually include additional information to the packets traversing into logical topology. And this way, without modifying the workload, the tenants can actually start to express new security policies at more high level without relying on addresses. So for instance, if the packet contains information about users or groups, one can express security policies in a very simple way without resorting to IP addresses. Now, I'm not going to claim that this is the killer application of network virtualization, but what is certain is that the network virtualization is already changing the operational best practices, and hopefully it kind of demonstrates how deep the implications of network virtualization can be. And I'm sure that there are more interesting implications of network virtualization. Thank you. Questions?
So, question about the virtual appliances that like the networking companies sort of want to build and put in the data centers and want customers to use them. Does it obviate all of that? Like, we shouldn't be doing that?
So you definitely have some appliances that you cannot implement this sort of a distributed way, because effectively what we are doing here is that we are implementing the basic L2 and L3 in a distributed way over the virtual switches. And there are some appliances that you cannot distribute. So I think you will continue to have your appliances. And basically what happens is that the appliance is basically a logical port. It's almost like a VM. You just route packets towards it. But there will be pressure to actually implement more and more services in a complete distributed manner. And we are already seeing this. So for instance, VMware already has a distributed firewall. It looks like a logical single firewall in the logical topology, but actually the underlying implementation is completely distributed across the hypervisors. And that actually has some nice, interesting implications as well, in the sense that previously you were not able to actually deploy firewalls in a very comprehensive way, because it might be so that you had some bandwidth limitations and capacity limitations with these boxes. But once the implementation becomes completely scale out, suddenly you can actually have within your logical topology firewalls all over, and you can actually increase the overall security in the logical topology.
Yeah, thanks. Good talk. Nadir from University of British Columbia. The last slide you mentioned about out-of-band header information, and in the paper you referred as a contextual information, I guess. I think it's very good source to use for network debugging. We could put additional information. So do you have any experience on it?
So we actually use those. There's quite a few bits within the encapsulation header you can use. And this sort of like extra information about the user and the workload is one way we can use that. But we also actually use heavily these fields for debugging. So you can introduce tracing information, troubleshooting information, and you can actually start to debug like real live workloads without actually breaking the workloads. So it's very convenient place actually. And there are lots of uses probably beyond these two use cases.
Yeah, that means you are already using it, right?
Sure.
Thanks.
Hi, Martin Kowalski from Amazon EC2. I wanted to get an idea of if you've looked at the performance implications of the software kind of switches, specifically with like 10 gig networks and 40 gig and going up to 100.
So there are several aspects that I completely skipped obviously in this presentation. And in the paper, we talk about the encapsulation and throughput, and we did a lot of work with encapsulation, optimizing the encapsulation on x86. But then there's also the aspect of classification on x86, which is kind of troublesome, as you know. And this approach we have obviously has implications in terms of classification. There's a lot of classifications we have to do at the first hop. So we heavily actually, Open vSwitch heavily uses flow caching for that purpose. So with flow caching and these tricks we did for the encapsulation, we are mostly able to avoid the issues with x86 when it comes to packet processing.
Rick Schlichting, AT&T. Are there any implications or lessons here for virtualization in the wide area? I know your focus was really on data centers.
You know, I haven't really thought about virtualization in the wide area sense that much, but what we are seeing is that often this sort of a deployments we have actually can span multiple data centers, but it's not really about virtualizing wide area networks, as I suppose you refer to.
Right, exactly.
Yeah.
Yeah. Okay, thanks.